Hey there, it's Shannon Magic Myers, and today we will be checking out section 11.6, surfaces in space. So the evil plan today is that we'll be able to recognize and write equations for cylindrical surfaces, quadric surfaces, and surfaces of revolution. So let's warm it up by doing something that you either had in Calc 1 or Calc 2, depending on where you took your calculus classes. And we want to find the volume of the region bounded by the graphs. Y is 4, X is 4, X is 0, and Y is 0, which has been rotated about the x-axis. And then we want to graph the resulting solid. So let's check it out. So Y and X are both bound from 0 to 4. So this would be our bound on Y for the lower one, and this would be the upper bound on Y. It's of our, actually, make that prettier. And then we'll have, for X, it's going to be bound these two segments. Cool so far? And then we've got our region here. All right, so we're almost ready to go, right? So remember the disk method, right? Actually, we'll be able to use geometry, but you've got this radius here, call it capital R at X, and then we wanted to rotate this about which axis? Good, the X axis. So we're rotating about this axis here. So what's that going to look like? Well, a lot of times what you can do is just sort of make an outline of what it's going to look like. So if you kind of go over here at Y equal to -4, that's the bottommost part of where it will revolve. And then you've got these other parts here. And then what will happen is it's going to go something like this. As it revolves. Not too bad, not too shabby, huh? So this is the whole evil plan, but what do we really have here? Anybody remember? Beautiful. It might be kind of lying on its side, but we have a right circular cylinder, correct? So what we would do here is, if you want to use the disk method, you certainly can. And if you recall, with that disk method, you would have your volume is equal to pi times the integral. Now be careful, since we are rotating about, about X, all right? And so this is kind of a so easy it's hard thing. So what we want to keep in mind are our bounds on X go from 0 to 4, correct? Because your change in X, remember the little rectangles that you would draw like so, and then you know these rectangles were from your original region, and this little part right here is dx, etc. Right? So how do we find our region? Well, what's the area under the curve? Right? We have this big R at X, dx. We've got those pieces, and actually, if you want the general formula, we'll just say A to B. Well, R at X is going to be this graph minus this graph, because that's the topmost first one's the topmost, second one's the bottommost graph, and that's how you're going to get the height of each of those rectangles. Dx gives you the base, and the height is each of those. And then by having pi there, you get your rotation, okay? So let's check it out. Plugging everything in, our volume will be pi times the integral from 0 to 4. Move that a up. And then our r of x is just going to be 4. We'll square that. Sorry, this whole thing is squared. And then integrate with respect to x. So our volume will be pi. And then what will we get? We'll get 16x evaluated from x is 0 to x is 4. So the volume will be pi times 64 minus 0, which is 64 pi cubic units. Now we could just use geometry, right? If you use geometry, we know that r is 4, right? And we know also that the volume of a right circular cylinder is pi r squared h. Cool so far? Well, what's the height of the cylinder? The height would be the total x. So it's going to be 4 as well, right? So our volume would end up being pi times 4 squared times 4. And that, of course, is 64 pi cubic units. Cool, cool? You feeling all warmed up? Awesome. Next up, let's take a look at this new definition of a cylinder. All right, we'll have some different wording. All right, and it's a different type of cylinder. So we're going to let C be a curve in a plane and let L be a line that's not in a parallel plane. Okay. Now, the set of all lines parallel to L and intersecting C is called a cylinder. C is called the generating curve, also known as the directrix of the cylinder, and the parallel lines are called rulings. Rulings, okay? Okay, so let's check this out. You end up having some sort of, generating curve, whatever it looks like, something like this. And so this generating curve, call it C, and if we kind of get it to be planar, so let's do something like this. And so this would make some kind of this plane. Cool so far? So our generating curve is this guy here. Generating curve is C. Now, L is a line that's not in a parallel plane, so it's going to intersect C. So if we get our L going on here, L is going to be somewhere like this. So this is L right here. And those rulings, okay, the parallel lines that are called rulings, all right, they're all going to be parallel to L. So these guys here I'm doing in the thinner. They're parallel to L, and these are the rulings. Cool so far? All right. So this one is L, and then all the other ones are, all the other lines are the rulings. Cool, cool? All right. So now let's take a look at equations of cylinders. So the equations of a cylinder whose rulings are parallel to one of the coordinate axes contains only the variables corresponding to the other two axes. Okay, so here we go. Let's take a look and let's take a look at these problems and check them out a little bit. All right, so here we go. Y is equal to z squared. So what does that mean? That means that our cylinder is in the beautiful, the YZ plane. Okay, so that'll be our scale where 2 of the tick marks is 1. And so now let's just kind of check out what we have going on. So our generating curve is going to be in the YZ plane, right? So if we, just kind of make our graph of our graph here of our, it's really a parabola, right? Let's see what we'll have. So we'll be at 1, 1. We'll be at 4, 2, right? And then it would reflect. Cool so far? So then now what do we have? We've got this generating curve, right? That's in our YZ plane, sorry. And X isn't in there, right? So X can vary. It's not going to have anything to do with happens to this equation. So I mean, you could shift this up by 4 or 2 or whatever, down by 2, and then you get your other curves. So you'd have something like that. And then, so what would happen is your line then, right, that we were talking about before, the line L is going to basically be what? Beautiful. It would be X equal to 0 is what L is from that formula. So your that would be your line, and then your rulings, right, are all going to be parallel to L. Cool? And then I didn't do the back part. Let's see. Pretty groovy, huh? All right, so anyway, I know we have a lot of technology now where we can, you know, make these graphs a lot quicker and stuff, but it's just kind of cool to take a look at them like this, I think, sometimes. Alrighty, so here we go. So again, this right here is our generating generating curve is in the YZ plane, and then our line L was the line X is 0. Cool, cool? Okay, so what about the next one? Why don't you try the next one? Z is equal to cosine at X. So where's our generating curve going to be? Beautiful. Our generating curve will be in the XZ plane. Okay, so let's see how you did. So here we go. Remember, now we're in this XZ plane. So here, when X is 0, you've got an output at 1, right? When, for the Z, when X is pi, we're going to be down at -1. Out here. And then when X is 2 pi, you'll be back up at 1. And where's our, where do we zero out? So we would zero out here and here. Good so far? And then zero out here and here. And when X is -pi, we'll be down at -1. So that's about here. All right, so assuming I did this one okay, we'll look something like this. Kind of weird, huh? At -2 pi will be up here. Cool, cool? All right, so then that, of course, is our generating curve, C. That was our generating curve, C. And then you'd have something like that. And what is our line going to be now? Beautiful. Our line is going to be y is 0 this time, so L is equal to y is 0. So that's our L. And so all of our rulings will be parallel. I don't know how great I drew this, but get what you get, right? Cool, cool, cool. All right, so there we have our maybe not my not so amazing sketches, but you get the idea. Now a quadric surface, the equation of a quadric surface in space is a second degree equation of the form, and it's second degree because some of the variables are squared. So you'll have ax squared plus by squared plus cz squared plus dxy plus exe, and notice you still have second degree for those middle terms there. fyz plus gx plus hy plus iz plus j is equal to 0. Now there are 6 basic types of quadric surfaces. So fortunately you don't need to watch me draw them again, painfully draw them again. But these are the ones, we'll go over them one by one. So we've got an ellipsoid, all right, and so, you know, kind of like it's similar to a sphere, right? But it doesn't have perfect circles in there. All of the traces are ellipses. So you can see inside all of these different ellipses inside, they're all called traces. Okay? So for each one, you'll have an ellipse, and then remember this means parallel to the xy plane. You'll have an ellipse parallel to the xz plane. And you'll have an ellipse parallel to, or ellipses parallel to, the yz plane. Cool? Okay. A hyperboloid with one sheet looks like this. All right. And you can see the equation here, it just differs by a minus at the end. So you're subtracting the z squared over c squared. So here, when you're talking about the xy plane, you've got ellipses. So an ellipse parallel to the xy plane. And then what's going to happen with the other ones? You're going to have good hyperbolas. For both your xz plane and your yz plane. All right, and then now if you've got a hyperboloid with 2 sheets, that means they're separate there. And notice the signs. In this case, the way it is, now you've got 2 minuses in between. So right here, the way this one was graphed, is that z squared over c squared is positive and the other 2 are negative. And so what's going to happen with these traces? So when you're looking at the xy plane, what are we going to have? Good, you're still going to have ellipses, right? You're going to have ellipses on that xy plane, and then hyperbolas on the other. Parallel to the xy plane. And hyperbolas parallel to the others. All right, moving right along. We've got an elliptic cone, okay? All right, an elliptic cone. Again, our trace in the XY plane is going to be still an ellipse, the ones that are parallel to the XY plane. And then the other two planes will be beautiful hyperbolas. All right, and our last two, we've got an elliptic paraboloid. And so this one, our trace to our XY plane is going to be an ellipse, right? And then what are we going to have for the others? The other two, when you look at parallel to those. So ellipse is parallel to the XY plane. And now we're going to have beautiful parabolas, right? Parallel to the XZ plane. And parabolas when we're parallel to the YZ plane. And then this one, a hyperbolic paraboloid, the one that looks like a saddle. Let's see what we've got. So in our XY plane now, when we're looking at the XY plane, what are we going to have? Good, it's going to be a hyperbola this time. And really, you know, these are, when you're parallel to the XY plane, these are really aids in graphing. This is why, you know, you're going over this. And then what will we get for the other? When we're parallel to the other two, we get parabolas, beautiful parabolas. Okay, so now let's take a look at drawing one by hand, and it's going to be, you know, we'll draw it by hand. I've shown you a bit about that free 3D graphing app. So most of the time we'll be looking at this kind of stuff, using technology. But let's give it a whirl, okay? So here we go. This one, remember, they're all positive. So this was the ellipsoid, right? Ellipsoid. So what we're going to have is, so this is an ellipsoid. And so let's take a look at the different planes, right? So if we want to deal with the XY plane, then that means that Z is 0, right? And then we would just end up getting what? Okay, so when X is 0, Y would be plus or minus 5, right? And when Y is 0, X will be plus or minus 4. And so our ellipse will look all right, so we got something like this on our XY plane. And then our xz plane, we would let y equal 0. And then what will we have? We'll have, again, x squared over 4 squared, but then we'll have z squared over 5 squared equal to 1. So when x is 0, z will be plus or minus 5. And when z is 0, x will be plus or minus 5. So that one will look sort of like that. And then, now let's take a look at the YZ plane. That would be when x is 0. So now we will have circle, right? In this case, because they both, so we'll have y squared over 5 squared plus z squared over 5 squared is 1. So we'll have a circle with radius 5 on that xz, or yz, sorry, plane. All right, and what does that look like? An ellipsoid. I'm afraid to dash more of these in, but you kind of get the idea. You could try kind of, sketching them in, shading them in, but here we go. You've got an ellipsoid. All right. So now, surface of revolution, if the graph of a radius function r is revolved about one of the coordinate axes, the equation of the resulting surface of revolution has one of the following forms. So if you revolve something about the x-axis, you get y squared plus z squared is r of x squared, and so on. When you're revolving about the y-axis, you've got x squared plus z squared equals r of y squared, and when you're revolving about the z-axis, you've got x squared plus y squared is equal to r at z squared. So let's go ahead and find an equation for the surface of revolution generated by revolving the curve z equals 3y in the yz plane about the x-axis. Okay? So since what function do we need? We're revolving about which axis? Beautiful. So we need to have a function of y. So we'll have r of y. Cool so far? Now, since z is equal to 3y, right, we can say r of y is equal to 3y. So, our equation therefore will be, so we'll have just x squared plus z squared is equal to, beautiful, 3y squared. So x squared plus z squared will be equal to 9y squared. And I think that wraps it up for today. Yes, it does. All right. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, please subscribe and tell your friends. All right. Bye-bye.